All right, so last time we talked about a summation for x squared. So how do we sum up from from index 1 to 4 of I squared? In other words, how do we do 1 squared plus 2 squared plus 3 squared plus 4 squared easily? And we could do it manually. 16 plus 9 plus 4 plus 1 equals 30. Or we could plug it into this equation. N times n plus 1 times n plus 0.5 all over 3. So it'd be 4 times 5 times 4.5 over 3. 20 times 4 is 80. 90 over 3 equals 30. It's not magic. The reason that works is because shapes work. If this is 1, I mean, this is not up to 4, this is up to 3, but this is 1 squared plus 2 squared plus 3 squared, and we put two of them together, it's going to leave this gap in the back, and a third one would fill that gap and leave this one extra thing on top, which if we divided it would fit perfectly into a shape that is 3 by 4 by 3.5. And if we took that same amount of volume and divided it into 3, we'd get what we want, right? So that was basically 3 times 4 times 3.5 over 3, which was the summation of index 1 up to 3 of I squared. Or what happens when we add up 1 squared plus 2 squared plus 3 squared, which was 14, and which here is 12, it's 42 divided by 3 equals 14. Okay, so what I wanted to do now is to see if I can apply this to integration in the same way that I did with the summation of I equation. Okay, so if you remember with the summation of I equation, it was just that the stairway, if we backed up from it far enough and had a big enough number, would make something that was resembling more and more, something more and more like a triangle, which would allow us to do x squared divided by 2, which is why the summation of x dx is equal to 1/2 x squared. Okay, and the same kind of thing applies for this shape, except that it becomes a little bit more three-dimensional. Okay, so I want to pose a question to you. If you had, instead of stopping at 3, instead of going 1, 2, 1 squared plus 2 squared plus 3 squared, we went up to like 200 squared. This thing would get pretty big, right? In order to see it all, we'd really need to zoom out. But as we zoomed out, this would look more and more flat. Okay? And it would look more and more like this. Imagine this is 200, we just had to back away from it. Or 1,000,000, and we had to back away from it. And the reason it would work like this is because we'd have each number squared. We have this square at the top, and the next level down would have another square, the next level down would have another square, and then we have so many steps, and almost an infinitesimal amount of steps, that it starts to look more and more like the shape. And this is kind of a weird lip here. This is the best I could do with Legos. But it makes these shapes. And what's cool about this is that instead of thinking of x squared as the standard graph, you can think about it like this, 1 squared is just 1, 2 squared would be 2 here, and everything in between would be represented by the size of its square. So instead of curving up, it would just kind of fill back. Okay. So anyway, where are we going with this? The integral of x squared dx, for anyone who's done, knows the power rule, you'd figured out that's, well, it's 1/3 x cubed. And we learned that, but we really don't know why. And I guess I just wanted to illustrate why. I'll do it in two ways. Number one, if we think about the summation up to like 3,000, and we use this equation, the n times n plus 1 times n plus 0.5. And by the way, I am going to be using this equation instead of the divided by 6 one, because I think this one illustrates the point better. That's going to give us 3,000 times 3,001 times 3,000.5 over 3. Now, if you're looking at that shape, remember, we can make a shape out of this. If you're looking at that shape, it's going to look a little bit different than this one, because this one is clearly rectangular, right? I mean, it has 3, 4, 3.5, and you can tell this doesn't look like a cube. But the bigger you get, the less that 1 or that 0.5 seems to mean. You're not going to really be able to tell that one side is longer than another side with that shape, with one side that's 3,000, one that's 3,001, and one that's 3,000.5. And the same thing would apply, but to a more extreme extent, if we had like a million, right? If we had a million times a million and 1 times a million 0.5 over 3, which is how you would model this equation. You wouldn't really even be able to tell at all that that wasn't just a cube. And so that starts to look more and more like just that divided by 3. And the same thing would apply if you took that shape and you just had, instead of making it every 1, it went down. It was like every half, and then every fourth, and then every 1/10, and then 1/1,000,000th it went down. It would start to look the same way. It would get to be like that, which you may notice is exactly what that is, right? And if you want to see this visually, imagine that this is the shape that you're trying to measure. I mean, what is the area of the shape if this is going from 0 to 3? And by the way, we know that based on integration, that would be 3 cubed, which would be 27 divided by 3. This is 9, assuming that the bottom here, that's 3, and that the height here would be 3 as well. But this is really hard to measure, right? I mean, do you just do, what's the tactic here? And what's cool about this shape is that there's a really easy tactic. And that is, if you put them together in the same way that you put the summation shapes together, they make a cube. And again, you have to imagine that these go to a point here. It would be a perfect corner there, and that there's not a weird kind of hump here in the middle, that it would be flat. But these fit together in a really cool, perfect shape, a cube. And what are the dimensions of that cube? Well, it would be 3 times 3 times 3. The area of this cube is just 3 cubed. And if the bottom here was 1,000,000, then the height would also be 1,000,000. And this would be 1,000,000 squared. It'd be 1,000,000 times 1,000,000 times 1,000,000, or 1,000,000 cubed. And then if you wanted to figure out what the area of one of those shapes were, you just 1,000,000 divided by 3, right? Or that 1,000,000 cubed divided by 3. So if you want to figure out what the summation of I squared from 0, or from 1 all the way to 1,000,000, right? We have 1,000,000 and then 1,000,000. Then you can just make a cube out of it. So take 1,000,000 cubed. If I can do it right here. 1,000,000 cubed, and then divide it by 3. That would get you the shape that you need. So summations can be cool because they help you to visualize it and see why that's the case. Great. Hope this was helpful.